learning about classification, but now we will learn using artificial neural network. I will start from a very basic artificial neural network. Okay. Okay, so neural network, basically, this algorithm, it is inspired from human brain system. We know that in our, I think Dr. Yogi know this better. Yeah, so in our human brain system, we have like, if the input comes in our nerves, okay, eh, yeah, and let's say we have a signal, input signal, then the input will be processed in our systems here, in our human brain systems. So then we know what is the meaning of that signal. For example, when we touch the ice cube, and then our brain will process the informations, and then we will feel, oh, it is very cold, something. Or if we touch a hot plate, then we will feel like, oh, this is hot. Yeah, so what happened in our brains, someone who's really smart, they try to represent, or they try to mimic this process into what they call it artificial neural network. Yeah, so it follows the neural system in our uh, brains. Yeah, so here in the new artificial neural network, similar with our neural system, so we have the input. The input will comes to the nodes. Nodes is, you can imagine, this is like this is the biological structure of our neurons. Yes, so here the input will go to the input layers. In the input layer, they are some nodes. Yeah, then the nodes here will process the input. So then it has the output. So nodes is the one that will process the input and give a new output here. The output from each node will be transformed into nodes in the next layer. Let's say this is a very simple, so we only have input layer, and then we have the output layer. Then we have the output. Okay. So basically the input layer, the main task here is just receive input signal. And then here we have in the next layer, the process input will be processed into the output. For more complex components, this is the structure of the artificial neural network, ANN. Okay, we have the input layer, we have some hidden layers. We can also have only one hidden layer, is okay. It's a simple neural network. If we have many hidden layers, then now they call it a multi-layer perceptron. Yeah. We have some hidden layers, and we have the output layer. Each layer will have some nodes. In the input layer, number of nodes depend on the number of input. Let's say we have two inputs, then we have two nodes. And we have k inputs, then we have k nodes. Okay. Maybe I will clarify here. The input, a number of input here doesn't mean that number of data. For example, if we have the data for like this, for example, this is attribute x1, x2. This is data 1, data 2. So means that the number of input dimensions, they are 2. So we have, this is input for x1, this is input for x2. Yeah, for each data. Okay. In the hidden layers, also we have number of nodes. This if in the input layer number of nodes depend on the number of inputs, in the hidden layer we can set any number of nodes. Yeah, of course, more nodes will, the structure will be more complex. But if you ask me, is it more nodes will give us a better result? Generally, yes, but then we have to come up with because more complex, the computational time will be higher. So the question is it necessary to use that complex structures? So that's the issue that we have to concerns. Okay, after the hidden layers, we have the output layer. Number of nodes in the output layers also depend of the number of output that we want. So if the output have only one dimensional output, then we only have one node. If we have more dimension output, then we have more nodes here. Okay, another component is bias. Okay, so each layer will have one bias. Bias functions here because sometimes in our data, okay, we have two attributes, for example. But the question is, are we sure that all factors that should be considered already included in these two uh, attributes? Yeah. Because we are not really sure about that. So that's why we add a one factor bias. So bias, let's say in a simple way, we say bias is something that are not uh, included in the input. Yeah, so we have bias factor here for each layer. Okay. Uh, Sorry. If you see here, there is one arcs. Oh no, I mean so many line here connecting each input to other each nodes to another nodes. So this the connecting part, they call it the arcs, and this means that it has the weight W is a set of weights connecting all nodes. Okay, so these weights will process the output from one node to becomes the input for the next nodes. Okay, so we have weights. So the main component in the uh, what is INN is the weights. Okay, then what happened in each node? Sorry. This is we discuss what is inside each node. Okay, so let's say this is for one node. In the nodes process in each node, we will basically we transform an input to output. Okay, then how to transform input to output? First, one node may receive many inputs. For example, like this, have maybe for this is from one node, second nodes, and then the third nodes. So this node itself, it has three inputs. Okay, so at the first time, we have to combine all inputs. So it is simple actually to combine all inputs. It's just like x1 times w1 plus this one. Let's say we have x2, we have w2, x2, w2, x3, w2. Yeah, so this is only the input, the total input for these nodes. And then how to transform all this input into output. So to transform, let's say this is I call it total x, for example. So we have a function that transform our input into output. So this function, they call it activation function. Okay. We can use many different activation function. For example, the simple one, we have step function, and then linear, sigmoid, tan H, ReLU, and softmax, and many others. Yeah, because uh, research in neural network is still growing, so I believe many researchers still trying many different activation function. Yeah. But But in general, after we combine all the input, then we use this function to transform into output. Okay. Nah, this is the example of the activation function. For linear problems, we can use, for example, binary step. This is step function and then linear function. Yeah, this is some picture for each activation function that we can use. Okay. Yeah, simple neural network. Basically, we can define it as like only have one input, one hidden layer, and one output. Okay, but now maybe you sometimes we hear what is deep learning neural network, the deep learning, because we have many hidden layers. So basically, deep learning, the basic one is the neural network. Yeah, but because the structure is very complex, due to many nodes or so many hidden layers, they call it now deep learning. Okay. Okay, so after we learn about the components, this is the basic process in the artificial neural network. In general, we have two main steps. The first step is forward step, and the second step is backward step. So what we do in forward step? Forward step, basically we process our input into the output. For example, here we have 4-dimensional input. Okay, so after the first layer, which is the input layer, receive all the inputs, it will transform into the hidden layer. Of course, don't forget, in each nodes they have activation function. So here we have activation function. This have activation function. Yeah. So each node have activation function. Okay. So here all the input data, all the input will be transformed into the hidden layer, process it by the activation function for each node, and then finally we have the output layer here. It means that after, let's say, we have X data transform into Y. Okay. So here the output is the predicted Y. So the predicted output. Okay, because why this is the predicted? Because this is the value of the output based on this neural network. Okay, so here, because this is the predicted, we can compare with the real output. So if we compare here or like this, yeah, we have some error. Okay, so what we want to do here is we want to minimize the error here. Minimize the error. It means that our predictions very close to the real value. Yeah. So the main objective of the neural network is to predict the output so that it can have a very small error, which is the differences between the real output and the predicted output is very small. Okay, so how to make the error is minimized? The one that what influence the error is the weights and what is the activation function. But basically, if we want to minimize the error, we have to find out what is the weights. So we have weights here. Okay, so the error here will be minimized if we can find the optimal weights. So here, back to weights. This weight, this weight, this weight. We have to find out what is the value of each weight. So then the output, or the error is very small. Okay, so how to how to guess, how to determine the optimal width. We do it using backward process. So the backward process is basically the objective is to minimize the error here by adjusting the weights. So backward, basically we do a weight adjustment. So for the next iteration, the error will be decrease. Okay. Okay. I repeat one more. So we have two main process, forward and backward. Forward is we process our input into a predicted output. Then, based on this information, the error information, we can adjust our weights. So then for the next iteration, the error will be decrease. Will decrease, yeah. Okay, so how to do this? Okay, sorry. Before that, learning process. So what I just described here, forward, backward, this is what we call it learning process. So if we sometimes you hear when you read about artificial network, neural network or deep learning, we will read about learning process. So learning process is basically this one. We ask this structure to learn the input data, so the weights will be optimal. Yeah, so the learning is updating the connecting weight to get the better output. Yeah, so we do forward, backward several times. It call it a learning process. Okay, okay, this one. Frank Rosenblatt is the one who proposed the Perceptron. Perceptron is the first neural network for computers. So this is the very basic ANN. Okay. Perceptron here, yeah, we have input layer processed by the weights, and then we have output layer. So this is the very beginning, very simple. So it has only input layer and output layer. Why it has a very simple? Because you can imagine in 1957, the computation is still expensive. So even to process this simple structure, maybe it takes hours to do this process. Yeah, that's why it's very simple. And also, the backward process at that time, it used a very simple backward process. So here, this is the mathematically representation of the forward and backward for perceptron learning algorithm. Okay, for example, we have weights, call it x. Yeah, so we have, for example, x I j. It means that the I is the data I, and then j is the dimension. Yeah. So for example, the first data, then it has x1 and j. J means dimension. So if we have two dimension, then we have x11 and x12. Okay, so we process from each xi first. Okay, for example, this is xi1, xi2 until xid, the d dimension. Okay, and we have the weights here, weights 1, 2, and until d. Okay, and of course we have bias. Bias is b is bias. So the output here, the output is this is the step function using a step function, for example, or you can use sigmoid, whatever activation function you can use. Basically, this is the functions, activation function. This is the input, yeah, using this equation, and then we transform into the WI output, predicted output. And then to update the weights, it only use this simple equation. So after we get the predicted output, this one, we will use the substitute this into this equation. So we can update each weights here. Yeah, very simple. The new weights for each weight equal to the old weight plus this one, theta, eta is the learning rate. Okay, learning rate, we can set our learning rate. This is like setting parameter that we use here. This is the differences between the real actual value and the predicted value. This is the error times the input. Yeah, it's very simple. Okay. Okay, so this is the perceptron learning algorithm. Basic, still the same actually. We do forward, we do backward several times until the stopping criteria is met. So here you can see that this one is the forward. This is the forward. Yeah, and this one is the backward. And we do this several times until stopping criteria is met. For example, we set number of maximum iteration, or for example, we set the convergence of the error. You can set any stopping criteria. Okay, so let's start with the example for the perceptron. Okay, so let's say we have 8 data. We have data 1 until 8 data. And each of them, we have 3-dimensional data, x1, x2, x3. And we have output. This is the output. Okay. Because we have 3-dimensional data, so we have 3 nodes in the input layer. So this one is the input layer. This is the input layer. Okay. We have x1, x2, x3. Okay, we have one bias and we have weights connecting all nodes, and we will have the output. Okay, we start from the first data. Let's see. The first data, x1 is 1. So input here is 1. And then x2, 0. x3, 0. Okay. So here, in Perceptron, activation function in the input layer is basically a linear function. So linear function, and if we have input 1, so the output is 1. This is, so it just receive the input. Yeah. Okay. So all this input will receive by the output nodes. Sorry, will receive by the nodes in output layer. This is the output layer. Yeah, this one is the output layer. Okay, so how to calculate this? Using this equation. And here, for this example, I choose a step function, binary step function, using like this. So if this input value is greater than 0, greater or equal than 0, then the output will be 1. Otherwise, it will be -1. Okay, so let's see. For the initialization, yeah, the first step is initialization. Of course, before we do this calculation, we have to know what is the initial value of each weight and also the bias. Okay, so bias set to 1 here. Bias is, I call it x0 to make it easy. Yeah, so x0 is bias equal to 1. And we have w0, w1, w2, w3. Okay. For the initialization, we use random number. Yeah. So here, if you ask me where I get 0.2, 0.3, 0.3, this is the random number. You can set any number. Okay. So for initiation, we set initial weights. Okay, so here we set the initial weights. Okay. Then we also have to set the learning rate. Learning rate. The learning rate value is between 0 and 1. Okay. So what we do in initialization is, of course, this we do it after we decide the structure. Yeah. Okay. Okay. In initialization, we have to generate initial weights and learning rate. Okay. After that, we can start from the first data. Okay. First data, we have x1 1 and x2 0, x3 0. This is the initial weights. Okay. So first we do the forward phase. In forward phase, basically we calculate all input here in the output layer. So here, this is the equation. Yeah, we have like for the first input, which is the bias first, we start from the bias. Bias is 1 because the input is 1, and we have like this. This one is 1 minus 1 times minus 0.2. Okay, and then for the first input, the input is 1. Okay, so it is 1 times the weights 0.3 plus the input here becomes the output of this node 0 times 0.3. The third input 0 times 0.3. Okay, so the result is 0.1. Okay, this 0.1 is only the total input for this node. Yeah, so if I divide it into 2, this is the input and output for this node. So this total input is 0.1, but we have to use the activation function. If the input is 0.1, so what is the output? We see from this, we have defined this. For example, for this example, let's see. If the input is less than 0, our input is 0.1. So 0.1 is here. Yeah, 0.1 is greater than 0. So the output is 1. So here, output is 1. This. That's why the predicted output for the first data is 1. Okay. After that, we do the backward phase. So in the backward phase, this is the equation. We do it for each weight. So we have 4 weights, weight 0 until weight 3, W0 to W3 here. We simply apply this equation. So then we get the new weights. Okay. Okay. So for example, the new weights W0 here will be minus 1. This one will be minus 0.5. This one will be 0.3, 0.3. Yeah. So here is the new weights. 0.1, minus 1, minus 0.5, 0.3, 0.3. This is the new weights.
Oh, wait. Dr. Farah, I got lost. 0.4 from where? That one? Sorry.
4.
0.4 learning rate. Is that the learning rate? 0.4?
Yeah.
Okay,
yes,
okay.
Right.
okay. That's why I get like, what is 0.4? That one. Okay, learning rate. Okay. Sorry.
Okay. Yeah, after we get this, and then we have the new structure is still the same, but the weights have been updated. Okay, so we use the new weights to apply the second data. Okay, The second data, do the same thing, exactly the same thing. So the second data, x1 is 1, so input will be 1, here will be 1. X2 0, so input 0, output 0, because this is the uh, oh sorry, maybe sometimes I show you. Sometimes in neural network books, they if they draw nodes and then they put something like this, it means that the activation function here is the linear, of course. So the fx is x. Sometimes you will see like this one symbol for f activation function is the step function. Yeah. Okay. Okay. So here for the input we still use linear. Okay. Continue. This one 3, x3 is 1, so the output is 1. Okay. So we calculate the total input in this output nodes. Okay, so we got this is 1. Bias always 1, yeah. 1 times minus 1. Second one, 1 times this one, minus 0.5. 0 times 0.3, 1 times 0.3. Okay, so the total input is minus 1.2. Okay, so in our output nodes now, we have minus 1.2. So the output is because this one less than 0, it means that this one will be minus 1. So the output will be minus 1. Okay, so predicted output for the y2, sorry, this is y2, means the data 2 is minus 1. Okay, and we do backward phase. Using the same equations for each weights, we do backward phase. Okay, so for W0, the original one is minus 1. And then we have 0.4 is the learning rate. This one is the real actual value 1 from here. And then this one, the predicted output is here. Yeah, this is the W2 predicted. Times this one is the input. So here is the bias. Yeah, this one from here, 0 here from x2, this one here. Okay, so these are the new weights. Okay, so point minus 0.2, 0.3, 0.3, 0.11. Okay, sorry. Okay, so for the next data, the weights will have the new weights. So here will be minus 0.2. This one will be updated into 0.3. This one still 0.3. This one 1 minus, 1.1. Yeah, we can use this for the third data. And then we do forward phase, backward phase, we get the new weights, we continue to the next data until all data, and then we can back again to the first data for the second iteration. Yes, so we run all data, it's only one iteration. We can do this several iteration until we think that, oh, okay, this is the this is the stopping criteria. Okay. Yeah. So finally, the final result, actually the last predicted output that we use, we can get that we get. Okay. Okay. What we just used, the equation, the example is actually the n problems. N problem is like this picture. So we have okay, for example, we have n problem. This one, the n problem if the output if the input is 0, 0, then the output is 0. If the input is 0, 1, will be 0. If 0, 1, sorry, this is 1, 0. If 0, 1 is 0, it will be 1 if the input is 1 and 1. Yeah, sorry. So this is the end problem. And very famous end problem, x1, x2, w, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. Yeah. If we draw this picture, we can easily see that, oh, if we want to classify the data, it's very easy. We can just draw one line, for example, this line, yeah, and then the data have already well separated. I call it well separated because in this area, the data is 0. In this area, data is 1. So this is well separated classification. Okay. Or if we use in 3-dimensional data, this one is dimension data. We also can use one linear hyperplane here, and the data already well separated. Okay. The basic perceptron algorithm that we just used, for example, like in our previous example here, is very effective to solve these n problems. Why? Because n problem, basically, this is linearly separable problems. What is linearly separable problem is the any problems, classification problems that can they can be separated. I mean, the data can be separated very well like this, only using one linear line like this. This is linear line. This one linear hyperplane because it is in 3 dimension. So this is linear hyperplane. Okay. Yeah, this is linearly separable problems, the easiest problems. Okay. But what happens if the problem is non-linearly separables? For example, this is Xor problems. In Xor problems, this is the value of data 1, 1, 0, 0. Okay. For example, we use one linear line to support this data. For example, we use this. Okay, let's see. This area, the data is 0. Okay, this for this area is okay. But let's see in this area. We have one data, the value is 1, but we also have 0 here. Okay. What if we change the line? We use another line. I draw here. Okay. If we use this line, okay, this area is okay because the data is only 0. But let's see in the above area. This data is 1, 1, but this one is 0. Okay, so this is not correct because it's not separated. Change the line. For example, we use like this. The same problem still happen. This area is okay, but this area is not okay. Still not well separated. If we change this line, also like that. Yeah. So this problem, if the problem cannot be separated only using a linear line or linear hyperplane, then the problem is not linearly separable, or they call it non-linearly separable problems. Okay, actually most of the problem is like this. It is non-linearly separable problems. So what we have to do if we want to use this perceptron algorithm, first we can add more layer. This is, I mean, hidden layer. What I mean is hidden layer. Yeah, we add more hidden layers, or we can use different activation function. Okay, so for example, in our in our first example, because there is the n problems, linearly separable problems, our structure for n is only input, and then we have bias here, and then output. This function is only using step function. This is for the n problem. This is linearly separable, so it is okay. But now, if the problems is more complex, non-linearly separable, we can add more layer. For example, we use, this is the hidden input layer, for example. This is the input layer, and we add one hidden layer before the output layer. Oops. Yeah. For example, we add one hidden layer. Or still not, if it is still not solved the problem, we can still add one more hidden layer. We can add hidden layer, or we can change the activation function. Okay. Let's see the example. Okay. This one, we have more layers. Okay. So we have first layer, which is the input layer. This is the second layer, is the hidden layer. If we have more layer, then we have hidden layer 2. And finally, the last layer is the output layer. Okay. The algorithm or the procedure is still the same. First, we have to generate initial weights. Okay. We do the forward phase to predict the output. And then we do the backward phase to update the weights. And we do this several times until stopping criteria is met. So basically, in all neural network problems, whatever, how complex it is, this is the main procedure that we use. Yeah, we have forward, we have backward. And the main part is in the backward, because backward is how we update the weights. More research, they trying to find out, for example, how to find the best updating rules, how to find the best activation function, for example. Yeah, because the main objective is how to update the weights in relatively short time, but the result is good. Okay, let's see for the XOR problems. This is the XOR problems. Yeah, still the same. First, after we have the structure. This is for XOR problems. I still use step function for the activation function, like this. Yeah, this is the step function. Yeah, step function. But I only add one hidden layer here. Okay. So the step is still the same, but how if we have more nodes? So don't worry, for each node, we just do it step by step, okay? This is the first data, okay? This one will be, bias is 0. It should be 1, but here is minus 0.2, yeah, okay. This is 1 minus 0.3. Okay, x1 0, x2 0. So here is 0, this one is 0. So let's see for the first node in the hidden layer. This one, we start from this node. Okay, for this node, there are 3 inputs from bias, from the first input, from the second input. Okay, so here, this is from the bias. Yes.
Excuse me, Dr.
Yeah.
Farah. So
Yeah.
0.5, negative 0.5, 0.8, and 0.7 are random numbers still because this is the first step. Is it correct?
Yeah, correct.
So
This
choose a number between 0 to 1 only, right?
No, minus 1 to 1, right? This one.
Yeah, minus 1 to 1.
Oh, okay,
Okay.
okay. Thank you.
But actually you can use any number. It depend on the input.
Oh, okay. Thank you.
Okay. welcome. Okay, this is the bias. This actually, I just make it simple actually, because this one is always one. Yeah. Okay, 0.2, and then 0 is from this, and the weight is 0.5. We get this for the input. So the output for this is 0. Okay, and we do the same thing for the next node. Yeah, we calculate, summarize all the input and convert using step function, and we get the output is also 0. Again, we do this for the next for the next nodes. We summarize all the input. We have this 0.3, minus 0.3, and then the output is 0. So the predicted output for the first data is 0. Yeah, this is for the first data, output is 0. So no matter how many layers, how many nodes that we have, this way is still apply. Yeah, so we summarize all the input. We have nodes. We just use summarize all the input, no matter how many it is, and then we use the activation function to transform, for example, to transform it. And if we have many layers, don't worry, we just do it one by one, step by step. Yeah, for what we just do from the first layer into the last layer. Okay, the repetitive procedure we do it. Then after that, we do the backward phase, still using the same one. Okay, yeah, we do it several times. Forward, backward, using this exactly the same thing. Finally, we will get the solutions. So this is the final. If you maybe later you can try, if you want. This is the final weights. Yeah, for the XOR problem. One example of final weights for the XOR problems. Okay, so then if I try to write, draw the picture, it illustrate the picture is like this. So because we have hidden layer here, we can have two linear line. So here we have the first line, and then we have the second line. So here you can see that this one is the data value 1. In the middle is data with value 0, and in the right side is data with value 1. So here our data has been well separated. Okay, because we have more layer, so we can have more line. Okay.
So,
Yeah.
Dr. Farah, this is really like I don't know, it's like an random randoming weighting. I don't know how you call it.
Yeah.
Is it correct like that? Like
Yeah.
okay, because it's different from the I would say that the decision tree, right? Because the decision tree is for me. When I
Mm-hmm.
review the class again, it's quite clear because the how is that we can have um the genie, and after that, like that's the reason how we make the tree, and now it's
Yeah.
actually really like a random random
Yeah.
weight. Is that correct?
Yeah. Oh, I forget. I think I should tell you. So, INN, neural network, they call it, this is the black box.
Yeah, it's so black.
Yeah, this is input, this is output. Yeah, that's why. So
I
what we
see.
do, yeah, that's why, because this is a start from random. Some research, they try to find out how to start with a good random, because yeah, I think for Advin ask me, what is the range of the initial random? Well, I can say it has, the range is actually, you can any range, but to make it more efficient, some research, they try to find a way to get a good random set. Means that, for example, this is the initial, for, let's say in the most extreme, from minus infinity to infinity. It's too large. So one research, they try to find out, instead of using very large range, why don't we focus on this range, which is the good one. nearby optimal value. Okay. And later we will try to update this random to make it a more represent the data. So that's why if we back to the early steps, what learning, we always call it learning in neural network. They call it learning because we start from the random value. Yeah, random is random. Yeah, we cannot say this is good, this is not. Okay, this is because we start from the random value. So the learning process is very important. Let's say this is the optimal point for the weights. We start from this point. This is initial. This is very random. So all the way to this optimal value, this is what we call it the learning process. That's why learning process is very important because we want this structure to learn and we train this structure to get a good result. Okay. Okay. Ah,
Dr. Ferris, sorry.
yeah, it's okay.
Can you please repeat the
Mm-hmm.
graph?
Which one? The
The
learning.
no no the last slide. Yes, this one.
This one. Yeah.
Yes, the graph.
Mm-hmm.
Uh, how were you able to create the two lines again? Sorry.
Oh, okay, because here we have one hidden layer. Let's say if we have, for example, at the first time, we have only one, even no hidden layer. Yeah, we only have input and we have output. I make it simple like this. So in this case, we can only draw one line to separate the data, like this, only one line. But here, because we have two hidden layers, sorry, we have one hidden layer here and one output layer here. That's why we can draw two lines, separable line.
Oh, okay, okay. Thank you, thank you.
You're welcome.
So if
Maybe
we have
mhm.
three, so there will be three lines like that.
uh
If the
not
layers.
not literally like that, but I can this the illustration.
Okay,
So
just the
some,
okay, okay.
yeah. So, okay, so maybe you have very complex problem, so maybe you have to get like this is the data 0011. So we have to do it. Oh, okay, this is very complex, so maybe we have more hidden layers because you need to have more lines. For example, we have this, we have like this, we have like this, we have like this, for example. So in this case, we need more lines, more nodes in the hidden layers. Okay. Okay. Okay, so Dr. Yogi already mentioned that because this is start from the random, so now our main task is how to make the structure have a very good learning process. Okay, so here, later after the Perceptron proposed, computation also becomes better and better, so we can have a more complex process in learning to learn the data. So someone proposed a backpropagation algorithm. Okay, so if we back to the basic perceptron algorithm, the weights is only updated by simple equation: weight plus learning rate, the error, and then the input. This is very simple, but this is not the optimization algorithm. This is actually just a approach numerical approach. So then someone proposed backpropagation algorithm. Backpropagation, they try to improve this backward phase. Instead of using numerical approach, they use this one, chain rules to calculate the gradient. I think if we back to our high school curriculums, high school materials, we know that if we have function x, then this, for example, this is the function x. This is x, this is f of x. I hope you still remember. Okay, so what is the optimal value of this function? Okay. Optimal value of this function if the first derivatives of the functions is equal to 0. Right? Why? Because the gradient is 0. Okay, so here, and then after we find the gradient is 0, then we can find out the optimal x, the point. Yeah, for example here, so this is the optimal value, which is the gradient in this point is equal to 0. Okay, so back propagation, it use this basic optimization theory to find out the optimum weights. The problem is, if we back to the neural network, let's say this is the simple one. This is the output. This is already at the output. Okay, let's say this is the output layer, or this is the output nodes. We have predicted y here. Okay, the only information we get is the predicted y here. But what we want to do is we want to find out what is the best weights here. So we used a chain rule. Chain rule is why we use the chain rule, because we have E is the error. We know the error is the differences between predicted value and the actual value. So this is the function of error. Okay, before we can derive using derivatives to get this W, we have to do this one first. Okay, so this one, the derivative E of W, we have to use it. We have to use chain rule because we want to derive from E to function of Y, and then Y is the function of Z. Z is what? This is the input. Yeah, and from this we can go to the W. So this is the chain rule. We do it step by step. Yeah, so only for the input layer, to get the what is the best value of the weights here, we have to do the chain rule from E to Y, Y to Z. This is the input, and then from Z to the W. Okay. Let's try for the example. Okay. Oops, sorry. This is the, I just use any example. Okay. We have, for example, this is the input data 1 and 2. Okay, only for the first data. And let's say this is the random initialization. And we have bias 1, bias 2. And then, of course, at the first time, we have to do forward phase. Okay, start from the forward. Okay, so for the forward, let's start from this one, H1, the first node in the hidden layer. Let's see, the first node in the hidden layer, first input is bias 1. And then we have the second input, which is from the X1, and then the last input is from here. Okay, so here bias 1 is 0 minus 0.5, W1 is 0.1, X1 is 1, this one, yeah, from this line. And then this one, input is 2, oh sorry, the weight is 0.3. Okay, so finally we have the 0.2. Okay, now I use sigmoid function. Yeah, so the function fx, here what we use the sigmoid. Okay, yeah, so after we get this, the total input is 0.2. using sigmoid function, I can get the output here is 0.549. This one. Okay. And then we do the same thing for the second nodes. Okay. We summarize all the input, and then the result is 0.5. And then for the output, we use sigmoid function also. So the output is 0.92. Oops, 0.992. Oh, sorry, 0.62, sorry. Okay, so
But
now...
Dr. Vera, correct me if I'm
Yeah,
wrong.
yeah,
What I know about sigmoid is actually 0 to 1, right? But what about
yeah.
minus 1 to 1? Can we do the
Oh,
sigmoid?
okay. Sigmoid
Yeah.
function is like this.
Yeah, minus 0 to 1. Yeah, that's what I know. So,
Yeah.
yeah.
So whatever value we input
Mm,
here,
mm.
the result will be 0 to 1.
Okay. That's the reason. Oh, okay, okay. Sorry. No, I got it. Okay, okay, okay. Yeah, yeah.
Because
Now I got it. So,
whatever value we have is 0
yeah.
to 1.
The result,
Okay.
right? Yeah, the result. Okay, okay,
Yeah,
okay.
the
Yeah,
result
sure,
is
sure.
0 to
Yeah, I
1.
got it. I got it. No, I got it.
Okay. And then the same one, the same thing here. We summarize all the input, and the total input is 0.8484, and then the output will be 0.7. Okay, so the predicted output is 0.7. Okay, and the real output is 0.6. Okay,
So sigmoid is
and
better. You mean like that's? It means like that.
no,
If
this
we see
one
like
I
that.
just use any number. I use any example.
No, no. I confused with the bottom that one. O equals to B2 blah blah blah, and then the other one is like we use the sigmoid. There are two numbers, right? 0.84 and 0.70. So we compare that one or
Oh, this one.
yeah, that why
Oh, yeah.
yeah.
This
I got
one
confused
is
in here.
okay. This one sigma of the input. So from here, this is the bias. This is W weight
H1, yeah, that way.
H1, 6 W6 and H2. Okay,
Yes.
so here the total here is 0.8484. But then we use the sigmoid function. How to write sigmoid like this? We use the sigmoid functions. So we add this one will be f 0.8484. If we put this number into the sigmoid function, the result will be 0.70023.
Why we have to put in the sigmoid? Sorry,
Because this sigmoid is the activation function.
active.
Activation function. So
I still
each
don't.
node,
I still don't get it.
uh,
Activation, yeah.
okay, it's okay, no problem. This is quite complex, so I also want to teach this slowly. Okay, let's pick this one. So each node, each node will first, all the output should be summarized. This until this part, is it okay?
Yes, it's clear. For this one, it's clear.
Okay, this one is clear. And the summarize is still only total input, not yet becomes the output. Okay, so how to transform from input to output? We have to use the activation function. Okay, the
Oh, okay.
activation function, now we in our example, the activation function we use sigmoid. Okay, so
Okay.
that's why the total input have to substitute into the sigmoid function to become the output.
It's always like that, right? We have to put the activation functions. Oh, okay, okay.
Always, yeah, always. In every node, we have to do this procedure. So we summarize all the input, transform the input into the output using an activation function.
Oh, this is still the forward phase, right? Still
Still the
forward.
forward.
Okay,
Yeah.
still the forward phase.
Mhm.
Okay. Okay. Can I see the XOR problem? The next one. I think the no. I think next one. Next one. I think this one. Yeah. XOR problem. The previous one.
Oh, XOR problem. Sorry.
Yeah. XOR problem.
XOR problem. This one. Okay.
Previous before this one. Before this one. Okay.
And
This one.
problem.
No. Before this one more.
Yes.
Yeah. Okay. This one. I cannot see the activation for this one.
Okay. For this one, the activation. This one is the input layer. For the input layer is the linear. The activation is linear function. So, for example, this one, linear using like this linear function, fx equal to x. So if the input is 1, f1, the result is 1.
Ah, I see. I see. Now I
Okay.
know. Okay. Okay. So
Okay. But,
this is for the okay. Okay.
and for this one, we use step function. So step function I define as this. This is the step function. If the total input greater than 0, then I use the result is 1. Less than 0, the result is -1.
Okay, now I got it. Okay, and the next one, the one that you explained for us is actually the
Sigmoid.
non-linear. You mean the next one?
Non-linear, right?
This is
Exactly.
okay. This one is non-linear. Okay, okay, okay.
Okay.
Now I really okay got it. I don't know for other
Okay.
students.
Yeah. Any question? If you don't understand, it's okay. You can ask me. I can repeat again. I understand this is quite complex.
But what? How we know that we use the linear function or the non-linear? How do we know that?
Okay. Okay. So for perceptron algorithm, because we don't need to calculate the gradient. For backward process in perceptron is only using this equation. Yeah. So we can use any function. We can use linear, we can use non-linear. It's okay. However, if we want to apply backpropagation, if we use for the backward, if we want to use backpropagation, yeah, we only can use that for this one. Why? Because, for example, step function, this function cannot be, it doesn't have derivation. So we cannot use backpropagation because the basic of the backpropagation is using derivative. So if the function cannot be derived, we cannot use that activation function. So please remember, for the backpropagation algorithm, we have to choose activation function, continuous activation function, yeah, not discrete activation function. Okay.
Okay. So that's so difficult. I'm like, well, this is really the black box. Oh my god, this is really.
I think after I learned this, I just thinking I think it's better to learn this right after we learn calculus, because the best idea
Yeah, I
of
think
this is
so.
calculus. But now I think we learned calculus many years ago, right?
Oh yes.
Yeah.
Yeah, I even forget what is calculus.
Okay.
Okay, now I think okay catching up.
Yeah.
Okay.
Okay.
And why is that cost function? You haven't explained yet that right?
Yeah. No, yeah.
Okay,
Okay.
okay.
What is cost function? Let's start with cost function. Okay. Cost functions is the function for the error. The function to calculate the error, because basically we have its predicted value and we want to compare it with the actual value. So the cost function is the error, basically to how do we calculate the error. Let's say maybe for example for the analogy, maybe we are more familiar with mean square error, someone using root mean square error. Sometimes we also use mean absolute error. Do you familiar with that? Yeah, so let's say this is a different, this is a function, basically this is the function to determine how we calculate the error of this forward process, how we define, how we measures the error or the performance of this forward phase, how different is our predicted value with the actual value. And this is the simple way. We just use a simple cost function. Okay. Okay. And we have the cost function and we have the cost value here. Okay. So now we can start apply backward using back propagation algorithms. Okay. If you if it is if not clear, you can ask anytime. Okay. So now we start backward from the last layer. So this is the output layer. Output layer, this is the hidden layer. Okay. So if forward, we start from the first layer into the last layer. Backward, we start from the last layer into the first layer. Okay. Let's see. In the backward, we have bias. We have weights here, W5, and we have also the next weight, W6. So this is what we are going to update: bias, the weights, and the 6 weights. Okay, so start from the weights first because it's easier. Okay, let's see. Here we have the information is the cost function E. So we have E here, error. Okay, from the error, we want to find the updated value for W. Okay, here from E, we have to back to the W to Y first. Okay, because E is the function of Y, and Y itself is the function of output here, input. Sorry, O is the total input here. You know. Okay. Okay. Maybe here I will write down first like this. For O, when we do the forward, O here is the summarize of the input using like this. Okay. And Y here is the function of sigmoid O. Okay. And E is the function of predicted output. This one, Y hat. Okay. So if we do the backward, we start from the last one into the first one. Okay. So here E is function of Y. So here we derive E of Y. So this is the derivation of this. Derivation of 1/4 W hat minus W square is this one. Okay. And then chain rule. Derivative Y over O. So derivative of sigmoid O is this one. W hat I times 1 minus W hat. Sorry, Y the hat 1 minus Y hat. Okay. And then O itself is the function of W. So here, from this equation, derivative O of W5 is only H1. So we use this value this value, like this. So here times this one times this one. We have already all the value here. Why I had is, I forget, 0.7, 0.07 minus 0.6, oh sorry, 0.7 here. 0.7 minus 0.6, this one 0.7, 1 minus 0.7, H1. H1 is this one, 0.5, 0.5549. And finally, we get 0.0115, this one. Okay, so this is only the delta, this value, delta for W5. Okay. I think for this part first, is it clear or any question? Do you still remember the chain rule for derivative?
No, I don't remember.
Okay. Okay.
But when I see that one, I think I don't know. I mean that's the derivative, right, from the sigmoid, right?
Yeah.
Yeah.
This is
Okay.
already what the
Yeah.
rules to
Yeah.
for the
The
sigmoid.
rules. Yeah. So now now it's kind of like it's been 12 years. Oh no, even more.
Okay. Any question? No. Is it clear? Okay. I will continue. So the same chain rules can be applied for the W6 if we want to calculate the updating step for the W6, this one. So here, basically we have E, and from E, we want to update W6. Okay, so because we get W6 from this, okay, so here W6 goes to submission, summarize of this one first. So using this equation, after that we use sigmoid. Okay, after that we use cost function. So to derive E of the W4, we have to do the chain rule again. So back from E into sigmoid into summarize of the input. Okay, so this one is here, still the same. This one still the same until this part. But here, because WO over W, derivative of O of W6 is, let's see, this one, if we derive of W6, the result is H2. So that's why this is H2. And then we substitute the value and we get this value. Okay. And then finally, bias. For the bias also, we have E over, this should be, sorry, this is typo. This should be B2. This should be B2. Okay. Okay, so this one, we do the same thing. The only difference is only this part. Why? Because O is this equation. If we derive over B2, so the derivation is 1. So this is the result. Okay, so this is the delta for W6. This is delta for bias 2. Okay, now we go to the first layer. So this what we have to do this is only for the hidden layer. From hidden layer, we have to go to the input layer. Okay. The procedure in general is the same. So if we now, this is our, let's say this is now in our position here. We see the output, sorry, the nodes H1 have input from W1 and W3. So we can update W1 and W3 using this equation. Again, we start from the E. So E, to reach the W1, E should be derived to the here first. Sorry, this one we sorry, yeah, for to this and here, and then to W5, and then to H1, and then to input H1, and then the W1. Okay, yeah. So this like this: WE to Y, Y to O, O to H1, H1 to the input of H1, and input of H1 into W1 using this chain rules. Okay. Then after we input all the equations of the derivatives, we will get the delta for W1. The same way we can update W3. Okay. And then
Dr. Fer, excuse me.
Yeah.
So it would be the result or the product of y hat minus y multiplied by up until W5 multiplied by H1 1 minus H1 multiplied by X1. That would be 0.0026, correct?
0.002. Which one? Oh, this one.
Yeah. So it's actually the product of derivative of E over H1 multiplied by H1 over. Oh, okay. So
Yeah.
all okay, I got it. Thank you.
Welcome. So this one is the result of this. This one result of this. One is the result of this. Okay. Yeah. So basically, actually the basic theory is simple. Like we just do derivative step by step. Yeah. But here again, now if we want to update W2 and W4, so we have E here. E should be derived into Y first, and then Y into O into H2, H2 into, let's say for W1, H2 into the input of H2, input of H2 to W2. So all of this, we times, multiply. Okay. Also for W4, to here. Okay. And also for the bias one. But remember, bias one connected to H1 and H2. So we have to do combination like this. So from E, derive to H1 first, and then H1 to input H1, plus E derive until H2, and then H2 over input of H2, and then summarize. This is for B1. Yeah, because bias 1 connecting to H1 and H2. Okay. After we get all of this delta, this is the delta for B1, this one, we will use the updating weight equations. Okay, so this one, the new weight equal to the old weight minus the learning rate, and this one is what we just get. This is the delta. Okay, so for example, W1, the old value is 0.1 minus 0.2 times 0.00264. Where is this come from? 00264 is the one that we calculate at the beginning. This one, 00264. Yeah, this. Okay, so finally we can update all of this. And back propagations, theoretically, it is better than only using the old perceptron updating weights. The old one is W equal to W U minus delta Y hat minus Y X. This is the old one. It just used numerical approach, but for back propagation, it used gradient approach. So it is more, yeah, it is better than the old one. Okay. Okay, but this is if we want to do it manually. Of course, for now we can do it using computers, so don't worry. But why I show you this, because I want you to, although at the end we will use a function package in Python, I do hope you can really understand what happened inside our black box. So it is not really black box, because we know, oh, this is the main process of this package.
Still a black box for me. Very black.
Very black. Okay, so if I can summarize, first we have forward phase is clear, right? Because it's just times input using transform. Forward phase, is it clear? Forward, we use input and then transform into output. Okay, and then the backward, basically backward is we update the weights many different way. Okay, so if we use back propagation, because many algorithms for backwards, basically they improve performance of back propagation. So at least in overall, you can imagine, oh, for backwards, if we want to update at this part, then we have to go from the last function to each step here. Okay, so it's like we do the same thing for the forward, but we do it using derivatives. Okay. Okay.
Okay.
Now,
Wait. Can I go back to the E for a while? For the double check. So the E for the before that one. Actually, I still get lost for the E a little bit. The E. Yeah, that E. No. Yeah. No, next one.
this one.
Mm, no. Okay. So the cost function is the Y. Okay, Y1, Y2. Okay, why we got it from the forward. Okay, why?
Yeah,
Okay, what about the other one? We got it from
this one, the real value, the data.
the data. Okay, okay. Because I keep looking at where is the another Y because okay, so that is
Yeah.
yeah. Okay. Because I okay now I know that the other one is just the data. Okay. It's basically
So
like error something, right? Yeah. See
yes,
the error
yes,
function. Yeah.
exactly,
No.
exactly error function.
Okay. Now I got it.
Okay. Okay. So yeah, forward, we get the predicted output, we compare our predicted output with the actual value of output, and then we use backward to update the weights. Okay, so now when we should update a weight, for example, if we back to our example, we have, this is the structure. First data, do forward and backward. In this case, the weights will be updated. Second data, forward, backward, updated again. Third data, updated again. In that case, they call it online learning. It means that for one that every time for each data point, we do one time forward and backward. Backward means update the weights. Okay. Uh, can you imagine if we have 1,000 data? It means that only in one iteration we do 1,000 updating weights. So if you can imagine like this, if we use back propagation, we have 1000 data, means that in one iteration we do like this 1000. For the next iteration, so 2000 times. Third iteration 3000 times. Takes time. Yeah. So that's why so that's why we have also batch learning. So in batch learning, we have this structure. Okay, first data we do forward, collect the error from it one that first data. Second data we do forward, we have error from second data. Third data we do forward, we have error for third data. Until all data forwarded, then we have the aggregation of error here. Okay, the total error, and finally we do backward. Okay, so we do only one time updating weights for all data. So if we have 1000 data in 5 iteration, for example, we only do backward phase 5 times. Okay, so we have online, we have batch. Online means one by one, batch means all together one update. Okay, plus minus. If we use online learning, the structure of the ANN, the weight of the network here, will always be updated based on each data. So every detailed pattern of the data can be captured in this structure. However, like you can imagine if our data is different, very different to each other. For example, this very large. So one data is here, one data is here, far, far away. So in this case, the weights is very difficult to convert to get convergence into one set of weights. Yeah, because for example, according to the first data, this weight should be 0.01, but according to the third data, it should be 0.9. So it's very, very far away. Right? Okay, so it's like always changing because the data is variation of data is very high. Okay, for batch learning, because we use total error here, so they only update the weights based on the general error of the data. Okay, so it's too general. The updating weights is too general. So between these two, between online and batch learning, we also have mini batch. So mini batch is combination of online and batch learning. The idea is because we also need to capture the details pattern of the data, but we don't want to let these weights always changing over the time. Okay, so they call it mini batch. So here, if we have 10,000 data, let's say we have 100 data, let's say we want them to divide it into 20 mini batch equal to 5. So for each mini batch, for example, data 1, data 2, data 3, data 4, data 5, we do forward and we collect all the error from data 1 to data 5. Then we do backward, update the weights. And then we continue with second mini batch data 6, 7, 8, 9, 10, do forward, and then we do backward. Yeah, so this one, mini batch, mean for each mini batch, we update one time. Okay. Okay, now this is the learning rate. How we set the learning rates. Okay. This is the idea of setting the learning rate. Let's say this is the function of error. Function of error, and the x, this is the weights. So the weights will influence the error. Yeah, we want to find optimal weights which can minimize the error. So in this case, the error is minimized. Now we want to find out what is the weight to get the minimum error. Okay, so if the learning rate, when we try to move into the minimum error, the minimum point, we start, of course, we start from the random weights. Okay, and how to move from this initial weights, for example, into the minimum, to the optimal weights. So this learning rate will, the learning rate will adjust our step size. Okay, for example, from this point goes to another point step by step into the minimum weight. Sorry, into the minimum error. Okay, so now if we set the learning rates too small, then our steps to get the optimal weight will be very slow, because we do it very small. Yeah, the step size is very small. So the error, if the error rate is too small, the error goes down a little bit. So means that maybe we need more iteration if we set the error rate is too small. However, if the error rate is too large, maybe we miss the minimum point. For example, this is the original one, original position, and then if the error is too large, maybe we can jump into this point. Then in the next iteration, because the step size is very large, so we go another point. So we will miss this point, the minimum one. Okay. So some algorithm, they try to use dynamic learning rate. Dynamic learning rate. It means that for the learning rate will increase. Will decrease if the number of iteration is increased. So the iteration is increased. It means that the illustration is like this. For the in the early iteration, still, let's say the weights, initial weights, is still far away from the minimum one. So let's make it a big step, because it's we assume that it's very far away with from the initial from the optimal point. Yeah, so for the early iteration, the step size is big, and then after several iteration, we assume that we're getting closer and closer to the minimum point. So let's use smaller learning rate. So for the further iteration, we set the learning rates become smaller. Okay, with the hypothesis that after several iteration, we are getting closer with the optimal point. So let's do it. Let's use small learning rate. Okay, we have dynamic learning rate. Okay, now. Because we are focused on the implementation, so we can use some functions that have been proposed by previous researchers. So for example, this is the easy one, the one that we discussed detail. Which one is the backpropagation or gradient descent? Okay, gradient descent is one of the backward process. It is very easy actually in terms of computational. It is easy. However, it may trap to the local optima. So this is the most common problems if we use the if we try to find out an optimal value using numerical approach based on gradients. May trap lock optimum, and of course it requires large memory. You can imagine in our illustration here, like too many things that we have to calculate. Okay, this is only one hidden layer. You can imagine if you have many hidden layers with many nodes and many inputs, so the process will be very, the step is easy, but it use many memories in the computers. Okay, and sometimes it's difficult to convergence. Another option, we use momentum. Momentum, the advantages is it converts faster than gradient descent, but need to select hyperparameters. So there have many parameters, so we have to find out what is a good parameter for momentum. And then third one, we have Nesterov accelerate gradients. Okay, so for this algorithm, they call it the advantage. They claim that the advantage is it will not miss the local. It does not miss the local optimum. But again, they have many parameters, so we have to set up more parameters. We have this one, ada GRA and or ada delta. This algorithm, or they already apply this one, dynamic learning rate. Yeah, the idea. So they can automatically change the learning rate. Okay. However, we need to calculate the second order derivatives. Why it becomes the disadvantage? Because in terms of computational effort, calculating second order derivative is quite uh, difficult, yeah, in terms of computations. Okay. And the newest one, we have ADAM, adaptive moment estimations. Advantage is fast and converts rapidly, and it's also vanishing learning rate. They adjust the vanishing learning rate, and they also have high variancy. But of course, because they have many advantages, it means that they have very complex algorithms, backward algorithms. That's why the computational will be much higher. Okay. Uh, I believe there are so many others algorithms for backward other than this, but I choose 1, 2, 3, 4, 5. This 5 because this 5, it has a package in the Python, so you can use this. For other algorithms, maybe the package is not yet available, so we have to code by ourselves. Okay. Okay. So this is the stopping criteria. Remember last week we talked about training and testing or validation. Okay, so when we have to stop, so we have to stop before it's getting have what we call it overfitting. Yeah, don't forget, this is last week I talked about this before. Okay. Okay, any question before I talk about input encoding? No questions? Okay, so I continue. Okay, I show you this. You can choose this from the package from the Python. And then what we have to do is input encoding. This is what we have to do. Even we use package in the Python, for example, we have to deal it by ourselves. Yeah, because the package, it has already, oh, this is what kind of structure do you want, what kind of activation function do you want, what kind of backward algorithm do you want to use. But the structure we have to adjust according to our input. That's why input encoding is important for us if our target is to implement. Okay, first, if our features are nominal features are usually represented using one of k encoding. For example, we have one variables. One variable, let's say type of car. Type of car. we have 3 different type of car, type A, type B, type C. So instead of using one input, let's say this is one input layer, and then the value maybe this is 1, 2, 3. So if we use it literally, so the input will be, if first data, the input of type of card is 1, so 1. Second data, the card type 2. Third data, type 3. This one will not get a better result compared with what we call it this one. We encoding our data according to the theory. Yeah, so for the numerical features, instead of using one nodes to represent all value, we break down our nodes into several nodes. Okay, for example, we have 3 value. So let's say this 3 value we encode using this. If for type car A, then it is 100, B 010, C 001. Okay, if we have, maybe we have a D here, so we have one more nodes. So 1, 2, 3, 4, or like this for A. For A is 1000, B 0100, C 0010, D 0001. Okay, yeah. So this is for the nominal feature, nominal attributes. Okay, and so one for each of these will becomes one nodes. So this is the input layer, node 1, node 2, 3, 4. Don't forget this one. This 4 nodes is only for one attribute, which is the type of car. Okay. How if our data is ordinal features? Okay. Usually the ordinal features can be represented using like thermometer encoding. For example, for small is 100, medium is 110, large is 111. How if we have extra large? Extra large we have 4, so we have 4 dimension, 1000, 110, 1110. XL is 1111. So it's like thermometer. We feel each bit one by one. And of course, each of these will be represented by one nodes in input layer. Okay. For real value, yeah, of course, we can use only one nodes. Yeah, so this is the basic one. The real value, one attributes represented by one nodes. But for nominal and ordinal, we usually break down one attribute into several nodes. Okay, so if our data, for example, we have x1 is a real value, and then x2 is ordinal value, small, medium, large. So our input layer will be like this. This is for x1, the real value. Second node, third node, fourth node, this is for x2, which is the ordinal one. And then we can combine all of these into the hidden layer. And then also the output layer. Yeah, so this is input, hidden, output. Okay, clear?
Dr. Farah,
So,
the
yeah.
real valued feature, can you please repeat?
Okay, real value if, for example, like income is the real value, or the what the demand value, demand is a real value, how many box for the demand, for example. Okay, price is the real value. So we can combine. Clear?
So only one value and then
One nodes.
okay.
So if we have x1 real value, x2 real value also, for example, then of course we have two nodes. This one first node for x1, second node for x2. Okay.
Okay.
Yeah.
Doc Farah,
Yeah.
so the values within each matrix for nominal and ordinal will be
Mhm.
dependent on us?
Yeah.
Oh, okay. Thank you.
Okay. You're welcome. Okay. Okay. So this is the basic for neural network. Yeah. Mm, before this, I think, yeah, I can continue first. Okay, I will show you for application for neural network, because I think for the code you can go to the Python package. It is already provided by the Python package, so it's very easy. Now I think I want to show you there are many different kind of neural network. What we just learned is the basic one. So we have input, we have hidden layer. Let's say we have hidden layer. Okay, and then we have output. This is the basic neural network.
So all of
Uh,
this just the basic.
yeah, this is just the basic. Okay. This is just the basic. Because the application, we can use many different kind of application using neural network. So there are so many research already developed many different neural network for various application. For example, we have this one, convolutional neural network. Okay, so convolutional neural network, at the first time it was proposed for image processing. Okay, focusly in image processing. Yeah, why? For example, like this. This is we give a picture into computer, and we ask the computer to identify what kind of, let's say we have a dog and cat. We give these two picture into the computer and ask the computer to guess whether it is a dog or it is a cat. Okay, so it is also classification, right? We give a one picture to the computers, to the CNN, and then it will give us the prediction if this picture is the picture of a dog or a picture of a cat. Okay, for us it's easy because of course our brain is much more better than computer. Very easy for us. Okay, this is dog. Yeah, this is what we see, but this is what computers see. So in computer, if we give one picture, then they will identify, read this as a set of number in each pixel. So each pixel will give one value, represent the color of a picture in that pixel. Okay, so for example, this is number 8. So the white one, 0, and then the most black is 251, 259, 229. Yeah, so what computer will see is the pattern of the value. Okay, like this. Now computers, you can imagine, or even right now the picture, the resolution of the picture is getting better and better. So you can imagine even for the, like this, the resolution is not good. This number 8, yeah, resolution is very low, but the computer already need a very big value like this. Yeah, so each pixels is one nodes. You can imagine each picture is one attribute. So in now maybe 4K picture, of course the size is very big. Okay, so what computer do using convolutional neural network is like this. The first one, from one input, they try to use a convolution layer. In convolution layer, basically, they cut each data and transform, like merge or make it compress it into a smaller array. Then the result is, for example, like this. Yeah, but still, because the picture, the size of the picture data is very, very big, so the computer want to squeeze it even more. So after the convolution, it use what we call it pooling layer to make it even smaller data. Then after that, we can give this input into the common NN. The common NN is just like this. What we just call it, what we just learned, like the back to the basic neural network. Okay, so this is the basic one. Then they can predict the output. So basically, CNN converts the picture data into a numerical data to predict what is the picture is. Okay, for more detail, for example, in convolution neural network, first, if we give them a picture, they will break the image into an overlapping image style. So they will cut the picture into the smaller pieces, smaller piece of the picture. For example, like this. However, don't forget it is a overlapping image. Okay, not like for example, we cut the birthday cake, so we cut it exactly like this. Yeah, there's no overlapping. No, not like this. We cut it into an overlapping image styles. So you can see in this, for example, like here, there is an overlapping between each pieces. Why? Because at the end, we want them to connect each other. Yeah, so that's why we should have overlapping part in the pieces of the picture. Okay, and then for each pieces, they will calculate, for example, like this. They use convolution filter to convert, for example, this is the input image. Yes, and they use what they call it convolution filter to to compress into the smaller one, to resize into the smaller one. Okay, it's basically in mathematically it's a simple operation. For example, this is the convolution filter that we use, and this is the original image. So this is 0 1 0 1 0 1 0 1 1. Okay, so first, for example, this is 3 by 3 dimension. So here, 3 by 3 dimension, we focus on this first. Okay, if we use it like a matrix dot product of this metric and this matrix. So 0, 1 to 8, so it will not use this. This is 1, so 97, we have 97. 0, we don't use this. 1, 37, so it plus 35, sorry, will not use this. This is 1, is okay, plus 25. 0, will not use this. 1, so we use 24, and this is 0. So summation of this is this value. Okay, and to get this, we use another overlapping part, another 3 by 3. Let's see, like this, 3 by 3. Okay, using dot product in mathematically. Yeah, Okay, so this is what happened in convolution layer. After that, our data is still quite big. So we want it to again down sampling the data. So here, if in the convolution layer we use dot product, in pooling layer we use sampling technique. So for example, we have the original data, 3 by 3 image, 3 by 3 array. We want to resize it into 2 by 2, make it smaller. So here, for example, again, we will divide it into overlapping array. For example, this is this part, yeah, and this part is the here, okay. This one is here, this one is here, yeah, overlapping still. And for example, we decided for the pooling layer we use maximum value in this area. So let's see in the first image 53H2, the maximum value is H, so we use only H here. The second one 3125, the maximum one is 5, so we only use 5. Again, this one the maximum is 9, we use 9. This one maximum one is 5, so we 5. So from matrix 3 like this, to 5 9 4 3, oops, 3, from this 3 by 3 matrix, if we use pooling layer, and it will change into 2 by 2 matrix in this value. Okay. We also can use average value. For example, find the average value of 53H2. We also can use that. Yeah, it's something that we decided which one you want. Okay. After the pooling layer, then we make it into flattening. They call it flattening. Okay, so why we need flattening? Because, for example, this is the result from the pooling layer, n by n feature maps. We see that in our network, neural network is like this. This is the input layer. Yeah, 1 2 3 4. So from this 3 by n, we use it flattening. Flattening is simply make it into n by 1 metric. So n by n, we transform into n by 1 matrix, because each of these will be represented by one nodes. Okay, so this one is 1 2 3. Second row is this one, 1 2 3. The third row is this one, 1 2 3. Yeah, just rearrange. Okay, flattening. And after this, already using the basic NN, the basic one. Okay, so this one to represent or to predict the picture. Okay, here don't forget the output. It can be also one output nodes or two output nodes or more output nodes. Okay. Okay, this one is convolution neural network, usually used to process image. Also can be applied for video. So for video, before we do this, basically video is we will cut video into a piece of a set. Sorry, we cut video into a set of picture. You know, video. So if we have a video, before we do CNN, from video we convert into a picture. And then for each picture, they call it time frame. Yeah, maybe one picture. For example, we have a 1 minute video, and we set the time frame is every 1 minute. Oh, sorry, we have 10-second video, and one frame is 1 second. So for this is until 10. So the first second is one picture, second is one picture, the third is one picture until 10. So for 10-second video, we have 10 pictures, and then each of them will be processed using like this. Okay. So we cut into some pictures. Okay, any question for CNN?
Actually, I'm doing CNN right now, Dr. Vera.
Okay, that's good.
Yeah, I'm doing CNN right now. And then can I ask how you say that
Yeah.
about actually the training loss? I would say that the loss function, okay, train loss. I would say that.
Yeah. Yeah. Is this a
Yeah.
training error? Yeah.
Yes, is that the training loss or the training error? Basically, that's the same, right? I mean
Yeah.
yeah. And then and what about the should we show the train loss and train accuracy at the same time?
Or you can choose actually. It is the same.
Because it's the
One.
same, right? Is it
Yeah,
almost the
it's the
same?
same.
Yeah.
You can choose.
Okay. So, but anyway, I have both.
Yeah,
Basically,
it's
like
okay.
okay,
It is
okay.
not the same thing. It is, but it inform us the same thing.
Yeah, it's all the same things. But anyway, the last I would say that paper actually it's better. You know, the camouflage is better using CNN. Actually, the result is much
Yeah,
better.
right. Exactly. Your camouflage is better using CNN.
Yes, the result much better rather than the meta heuristics, even much better. This one.
Of course, of
Yeah,
course.
yeah.
Okay. Okay. And then I also will introduce you recurrent neural network. Okay. So if CNN used for image processing, RNN basically it's used for prediction. Okay. Why? Because they call it recurrent. So why they call it recurrent? Because the output will be used for the input for the next data. Okay, so let's compare. This is RNN. This is the basic neural network. Yeah, in the basic one we have input. This is input. This is the process of hidden layers, and we have output. Okay, but for RNN, our output is not only becomes an output, it will be used again back to the system as the input for the next data. Okay, so for example, like this is fold one, and if we unfold this, for example, let's say we have this is time series, yeah, this is time series data. Okay, this is the t is the time, t minus 1. If we have t minus 1 data and process using nn, then we get the output, which is the predicted value for of the t minus 1. And this value, of course, we are going to use it as the input for the next periods. So that's why instead of only becomes the output, it will also become the input for to predict the next output. Okay, again, also for the t plus 1. For the t plus 1, the input is also from this, the previous value. Okay, or for example, like this. Okay, for feed-forward network, usually for example, the problem is uh, I want to guess what uh, what Dr. Yogi will eat. Depend on the weather. Depend on the weather. If it is rainy, then it will eat some soup, Indonesian meatball soup. Okay, but if it is sunny, then he will eat ice cream. Okay, so the input here is the weather. Yeah, whether it is sunny or it is rainy. Okay, and what will Dr. Yogi eat? Okay, this is a common neural network. Okay, but for RNN, recurrent neural network, we are going to guess what Dr. Yogi will eat depend on what he ate before. So for example, sorry, this is all Indonesian food. I forget to change to international food. Okay, let's say on Monday, he will eat fish cake. Okay. Tuesday, he will eat some meat, grilled meat. Wednesday, he will eat soup. Yeah, soup. Thursday, eat ice cream.
You make
Again,
me hungry,
Friday.
you know.
Yeah, that's why I always use food, for example, because everyone loves it. Okay.
Especially the fish cake. That's so yummy. That's my
This-
favorite.
okay. Okay, so in RNN, we will guess what Dr. Yogi will eat based on what he eat before. So here we have the data, the pattern of what he eat in 1 week from Monday to Saturday, for example. Okay, let's see. So Monday, he eat fish cake and we give this as the input into the RNN. Then the output is meat, for example. And Monday to Tuesday. So we use that data for Monday to predict the output for Tuesday. And then we use the output, this one, as the input to predict what will be eaten in the Wednesday. Okay. So, and then we still use this. Wednesday result will become the input to predict for the Thursday. Okay. Thursday will be used as the input to predict for Friday. Friday used to predict for the Saturday. And finally, Saturday, what will uh, he eat in Sunday? Yeah. So during this step, our network here is always be our network learn from the pattern. Monday, Tuesday, get the pattern here. Tuesday, Wednesday, updated the pattern. Wednesday, Thursday is learning again. Thursday, Friday, learning again. Friday, Saturday, learning again. And finally, let's say this is already well trained RNN. So it can predict if Saturday you eat fish cake, what Dr. Yogi will eat in Sunday. Okay, so this is recurrent neural network like this. Okay, any question for RNN? No questions? Okay.
No, sure.
Okay. RNN, if we further improve, for example, yeah, we should be creative with the neural network. Now, I want to make a more accurate prediction. So, I want to guess what Dr. Yogi will eat, not only based on the what he ate in the previous day, but also according to the weather. So we have two different type of input. The first input is time series. Okay, the time series data. So of course the output here will become the input. So these three, for example, let's say these three input is the recurrent input. But I also combine it with the data of the weather. So the weather have another input. And of course, this input is not from the previous output, no, because this data is just the weather data for that day. For example, this is for Sunday. We want to guess what will he eat in Sunday. So this is the prediction from the Saturday, and this is the weather for Sunday. Okay, so we can combine like this. Okay, this one, Ferrous Architect for RNN. So the one we just, this one is 1-to-1 structure. 1-to-1 means that we have, if we have only like this, it is 1-to-1. So from 1, we predict 1. Okay. So we have data for Monday, we want to predict for Tuesday. Okay. We also have one-to-many. So we have only Monday, for example. Then we predict for Tuesday, Wednesday, and Thursday. Example of this. Now I believe our cell phone, if we turn on the predicting texting, for example, if we just type like TH, then our cell phone already, sometimes it will give you suggestion, oh, do you want to write thanks like this, for example. So it means that we have one input to predict the next 3 output. So text prediction use this kind of architect. Okay, we also can use many-to-one. Usually for time series, we have data for Monday, Tuesday, and Wednesday to predict Thursday. Okay, we have one data time series for 1 year, 12 months, to predict the next year data, for example. Okay, we also may have many-to-many, combination of this. Okay, better before this. I think I also want to, they are also different. Maybe you can, I need some space. Okay, you also can use restricted, how to write, restricted Boltzmann machine, RBM. This is also based on neural network. But here, input is also the output. Okay, so input is also the output. So here we have input layer, for example. This is input layer. Okay, and then we have hidden layers. This is hidden. Another hidden layer, for example. This is fully connected. Okay. So the training and so the forward and backward, they do it like this because this is input as well as the output. So forward, backward, forward. So it is all to train all of this. So forward is up, down, backward also. When we use this, for example, if we want to predict rating of the movie, for example, or for example, if we usually buy books in Amazon Books, for example, sometimes the Amazon will give us recommendation. Do you also love this book, for example? Yeah, because why sometimes they give us recommendation? Because they learn from our behavior. For example, if we usually like a book for fiction or fiction books, so they will give us another suggestion for fiction books. Yeah, this is input becomes to the output. They will give the prediction of a rating of books that not yet get rating for ourselves, for example. Yeah, so there are so many different architecture of RBM. Of neural network. And I believe until now, even researchers still study about that. They still keep proposing the new one for neural network. Okay, any question? Please, if you have questions. for the Python package, you can use, wait, I try to open my browser. Okay, any questions? This one. You can use this in the Python. You still using scikit-learn for the Python. And this is the multi-layer perceptron, a basic one. Here, you can use this for classifications. Okay, here, if we click this, okay, this you can adjust the parameter for your structure. For example, the first one is number of hidden layer size. So here we can set how many hidden layers and how many nodes in hidden layers. How many nodes we are going to use in our hidden layers. Okay, and then they also provide us with several activation function. For example, this is the identity. Identity is the linear one, like this. Fx equal to x. And logistic is the sigmoid, basically. And tangent h, hyperbolic tan h, this one. And relu, this one. Solver means the backpropagation algorithm that will be used for our neural network. For here, they provide LBFGS, which is the quasi-Newton method. This is the basic one for backpropagation, actually. And also we have stochastic gradient descent. Adam, they give us this one. This one is the penalty for regression parameters. This is the batch size if we want to use a mini batch. Okay. This one, if we want to specify the learning rate, okay, we can use constants, which is the start from the first iteration until the last iteration, the learning rate will be all the same. Inverse scaling, ENV scaling, this is gradual decrease the learning rate. Okay. And adaptive is the learning rate will be this one. They use adaptive means that the learning rate will be keep constant as long as the training loss keep decreasing. So the assumption is like this. Oh, the error is still decreased. So we have used the correct learning rate. However, if until 2 iteration, the error cannot decrease, then they will change the learning rate. Okay, so they call it adaptive. Okay, we have initial learning rate, maximum iterations. This is the random states, momentum. This is only parameter if we use SKD, and some others parameters. So there are so many parameters in neural network that you can explore this actually. Okay. Yeah, this is the example. If you want to try, you can try using any data, benchmark data. Yeah. Okay, so this is one basic package we can use for MLP. Okay. Any questions? No questions? Okay.
No, sir.
Yeah, okay. Let me back to slides. Okay, so for the classification, we have talked about that. We have discussed about data classification using decision tree and this one using neural network. So please, I want you to try apply data classifications. So this is for the first assignment. You can use any supervised benchmark dataset. Yeah, just use benchmark dataset because in benchmark dataset, they already have the actual class. So it's easier for us to learn and to test whether our algorithm already correct or not. And then after you find some benchmark datasets, you can apply, please apply one data classification algorithms. You can choose decision tree, you can choose neural network, or you can use both of them. It's up to you. And don't forget to do data processing if it is necessary. Yeah, because some data maybe have a missing value, some data, I don't know, there are so many different condition with the data. Yeah, so please check the data and do necessary data pre-processing. After that, you can do data classifications and perform validation process. Validation process you can use, for example, a k-fold cross validations and give the result analysis, interpretation or analyze the result. And you can submit your report. A freestyle is up to you. Sorry, not March. I mean April.
So March 10 next year, right? 2022.
Next year. No. Let's see. 2 weeks from now. April, yeah.